All right, let's get started. Who'd like to offer a prayer for us? Thank you. Amen. Thank you very, very much. Go ahead and look over here. Make sure you get the homework assignments. Exam starts tomorrow. It's in the testing center. Goes through Monday. Monday's a late day, so it's going to cost you money. We don't cover section 3.4, so the next section we cover is 3.5. It's a really big section. Lots of new ideas in there. We take 3 days to cover that. So we're going to do the first part of 3.5 on Monday. So you have that to do while you're preparing to take the exam. Anything else? Oh, yeah, and if you don't have a partner for the cryptography problem, where you're going to pass the code back and forth, you can email the TAs and they can help to line you up with other people that don't have a partner. Okay, any questions about the exam or homeworks or anything? Okay. I'm going to do a few things by way of review, and then I'll turn it over for questions from you. If you guys don't have questions, then I've got problems like the one that was on the board. Okay, so this is there's a common problem in robotics and animation when you're controlling things at joints, like by angles, and you know where the end of like an arm should be, and you've got a shoulder joint and an elbow joint and a wrist joint, and you know where you want the end, but you don't know what angle each of these should be. And sometimes there's infinitely many possibilities, right? I can keep my finger there and still move. Come on, finger hold still, right? I can keep my finger at that point and still move these around. But this is a very important problem to solve. It's the inverse kinematic. They use what's called inverse kinematics. And one very simple solution is using math with everything you've learned so far in linear algebra. You can work on this problem, at least in the 2D, or if you have three things, 3 angles or 3 sections of the arm, and you're in 3 space, then you can do this. So this is the setup I have for, basically I have a shoulder joint and an elbow joint. So here I can move this piece around, and I can adjust the angle here. So, and the goal is to get B, the end of the arm, right here, this red spot that says goal. Okay, you can see I have a light vector there showing like that's where we need to move. So to start off, think about if you increase this red angle, what direction is B going to start moving in? And if I increase the blue angle, what direction is B going to start moving in? Okay. Now, of course, if we move it a lot, B is just going to move in a circle. Right? It's going to move in an arc. But right at the beginning, it's going to move almost in a straight line. Okay. Thinking kind of like the derivative idea here. Right at that moment, which direction is it heading? And that's what I'm after. We want that right at that moment, right at the beginning moment when you start to change the angle, which direction is it moving? So talk to your neighbors and see if you can figure out which direction B would head if you increased this angle. Increase means in this case, increase, you're going to get more red, so you're bringing up this way. And if you increase this angle, so you're going to be widening that. Okay, so talk to your neighbor, see if you can figure out which direction those would be facing. Those would be moving B. All right. Okay. Someone tell me about the red angle. So about what direction? You can just use your arm to try to imagine, like if your elbow was at B, point in the direction. You can all do this. Point in the direction you think that B would be moving if your elbow was at B. So you can move this whichever direction you think it would go. So not a lot of people are doing this. Come on, take a guess, take a stand. So see a lot of people like this. Okay. I heard one person talk about orthogonal. Okay, so there is this, it's going to be orthogonal to this thing, right? Because if I increase that angle, this whole thing's going to move, right? And so the movement's going to be orthogonal to this guy right here, this dashed red line. So it's going to come right there. Okay, so that's going to be the direction. How about if I move B? Sorry, if I increase A, what direction, that blue angle, what direction does it go? Point to the direction, if your elbow's a B, which way is it going to go? So, okay, now I see a lot of people pointing down, although a few people are still going like this. Yeah, so when you just initially start to change this guy, it's going to be coming this direction, perpendicular to this segment there. Okay, so we work with perpendicular and orthogonal. They just come up all the time when it comes to moving things around or forces and such. We have a whole chapter on it coming up near the end of the semester. So this vector looks like it's about a 2, -6. So what would the vector of the orthogonal vector be? So 2, -6. So this is like a nice, we're doing this as to review, right? So what's an orthogonal vector to 2, -6? Right. You need to pick something here. We can take the dot product and get 0. Yes? 3, 1. So 3, 1, 6, -6, add together to get 0. Nice. Okay, and that's so 3, 1, which direction is 3, 1? So I'm going to go 3 this way and 1 this way, and that makes sense. Okay. Okay, so I can show you what these vectors are. So there's the u vector, there's the v vector. That's with a change that I think is 1 radian. So about, if I change it in 50 degrees, if they kept going in that direction, that's where it would be for each of those. So pretty far. But I want to get to here. I want to get to that red dot. Okay? So now the question is, how much of this direction and how much of this direction do I need to get there? How much am I going to move the red? How much am I going to increase or change the red? And how much am I going to change the blue to get to here? Now, I'm not going to do it all at once, because it might mean big changes. It's not going to stay in that line. But at least I can get it closer. Right? So I'm going to take a small step. But even to do that, I have to know how much of this vector and how much of this vector I need to equal this vector. That is exactly the peanut butter and bread problem. If I have a dietary goal of protein and fat, and I want to know how much peanut butter I need and how much bread I need to get to that goal, the mathematics is exactly the same. Okay? So how much peanut butter, how much bread do I need to get there? You can write that down as a system of equations, or we can write it down as an AX equals B system, where A is the U vector and the V vector. It's this matrix. So which one is which? Well, this is the only one with the negative component, so that must be V, because V is going down in the Y. So it goes over in 4, down about 3. U goes over at about 5.5 and up almost 2. Okay? So I need to know how much of each of those. How much of 5.68 and 1.78, and how much of 4.04 and negative 2.95 do I need to equal? I need to equal this vector. So I have to take the difference from goal. I'd take goal and subtract B. And I've already done that. It's right there. To equal 3.22, 6.68. And of course, I could rewrite this as the way I have it up there. That times xy equals 3.22, 6.68. So how much is x and how much is y? How much of this vector and how much of that vector? I want you guys to think, in this particular example, about how much of u and about how much of v do I need to get to goal. So just kind of approximate, using the image over there, about how much of u and about how much of v. You can talk with your neighbor. Share your answer with the neighbor. All right. Someone got an estimate for me? Joseph? 2u and minus 2v. So 2u, I can think about getting 2, going out here twice as far. So I'm out here somewhere. And then a minus 2v, and maybe that's about the same direction. So I can think maybe that is about 2 of those, seems like. Okay, nice. Someone else have something different? I'm not sure. A lot of you probably had something different, but something around there seems like it would make sense. Turns out to be this guy right here. So you said 2, it's 1.5. So you get here, and then that's not quite the same, not quite as long. So about 1 1/3 in the opposite direction, because we got to go that way. You can think about it the other way too. We can start with the negative u and go this way until we get on a path that's parallel to u, and then go back. I have that on here. Let me pull it up. There. So that goes the B first, and then the red. Sorry, the blue first, and then the red. So, okay, so that's, but to solve this system, the easiest way to do it is with a 2x2. What's the easiest way to do to solve this with a 2x2? Braden, you can do your sign language. I'm just kidding. Out loud. Yeah, find the inverse. We have a nice formula for how to find the inverse of this. So we can find x and y by taking the inverse. So take the inverse of this guy. So, and put it right there and multiply. Really slick way to find the system for the equation of the 2x2. So that's how I found those numbers. So Sammy, you want to get me back there? Thanks. So that's how I got this 1.53. I found the inverse, and then I had just GeoGebra do it. So find the inverse, multiply by that b, and it says 1.53 negative 1.35. And now I make the change. I use that. This tells me how much I should change each of those angles. As long as I change them in this proportion, I'll move almost along that purple line. So the first one is the red. So if I think about degrees, that might be easier. I could do 1.5 degrees in one and a negative 1.3 degrees in the other. That's not very much. But let's 10 times it. I could do 15 degrees in one and a negative 13 degrees in the other. So I'm going to do that right now. I'm going to hide these. Okay, so I made a small change. But now I'm in a different position. My values have changed. I just do it again. So now I should change the red by about 13 or degrees and the red by a minus 9 degrees. And now I get new changes. And you just keep doing that, and look what happens. And oh, that's kind of moving it back there. Let's find a nice, oh. That was cool. Yeah. Your arm doesn't quite do that, right? You don't go like this and then all of a sudden, but so the mathematics that I used to do this, I only used mathematics you guys have learned so far in this class. Like this is all within your range. If we were to sit down and walk through like everything I did to program this. I thought it's a cool application too. So, oh, I really want this up. Okay, so everyone think about these two questions. You can talk to your neighbors about it. What do you think about these situations? The question are in either of these situations, can you say that that one of these columns in the matrix are always linearly dependent? Okay.
On the other one, couldn't you just uprip the first matrix with the answer in itself or something? Do you have to do the inverse
On the first,
like on the
All right. Okay. We're going to do thumbs up. Everyone listen to the rules of the voting, okay? So thumbs up are, the columns are always linearly dependent. Thumbs down, they're always independent. Thumbs sideways, we don't have enough information, so it could go either way. So for number one, are they always linearly dependent? That's thumbs up. We're not sure, thumbs sideways, always independent, thumbs down. So let me see your thumbs. Okay. This is, yeah, for the first one. I should have put numbers on them. Okay, lots of thumbs sideways, a few thumbs down. Okay, that's thumbs sideways is the correct answer there. Okay, how about for the second one? Given a 3x4 matrix, where the column's always linearly dependent. So if you're saying yes, the thumbs up, we're not sure, so it could go, some situations could be dependent, some could be independent, go sideways. If they're always linearly independent, thumbs down. So show me your thumbs. Okay, lots of thumbs up, good job. Okay, this is something that the TA said that on your homework people were struggling with, okay? So especially that first one. So here's an example. So I picked an example. This 3x3 is what we were working with yesterday. So that I know is, I can row reduce to the identity matrix. So if I row reduce, I get this. Are these independent columns? Yeah, even though I've got this row of 0 here, that's okay. I have a pivot position in each one of these. So this is okay. I'm independent. Okay. One way to think about this is I have 3 vectors in R4. So I have 3 vectors in R4. Can each of those be independent of the other ones in R4? Is that a possibility? Yeah. I can pick one vector. The span of that is on a line. Pick the second vector, as long as it isn't on that line, I'm good. Those will be independent, and now I have a plane. The span of both of those are on a plane. If I had my third vector, then I just have to make sure it doesn't go in that plane, and they're going to be independent. That's fine. Yeah, it's okay to have this row of zeros here. That's just fine. But the 3x4 matrix is different. If I think about these columns, I've got 4 vectors, but I only have R3. I only have 3 dimensions. And best case scenario, at least my first 3 are all independent, but no matter what, my first 3 are independent. I span R3. So I can get to any possible place. I can use those 3 to construct any vector in this space. But that last one, no matter what I add here, I can already get to that with these. So I can find some combination of those first 3 to get that one. I might even end up, it might be that I only have 2 independent vectors here, and then I can write both of those other ones as the first 2. That's also a possibility. But I know there's no possible way that these could be independent. Okay? And I don't get a row of zeros here. And I don't, I get something over here. Who knows what it is? But yeah. Okay, questions on that? Okay. So just because we get a row of zeros doesn't mean that the columns are independent. It would mean that the rows are independent. That these 3 row vectors, if I think about the row vectors, those row vectors would have to be a dependent set. Because again, I'm only in 3 dimensions for each of these, and I've got 4 of them. So, Seth?
So in general, if you ask us if the matrix represents something that's dependent or not, generally it's just columns. Like that's all we care about.
So his question, for those that were online, when you give us a matrix and ask us if something is dependent or not, is it always columns? It may not all be always columns. Most of what we've done so far has been columns. Okay. Yes. So yeah. So it'll be in the problem, or in the context. In real life, you'll use your context to understand which ones you care about, right? But yeah, if there's not a context on the exam, we'll tell you. So whether the columns or the rows. So if these aren't the same, if the dimensions aren't the same, then either the rows or the columns are going to be some independent set. If it's square, then if the rows are independent, then the columns are independent. If the rows are dependent, then the columns are dependent. So, okay, great question. Other questions on this? Okay, one quick thing. Oops. Maybe. A lot of your homework, the TA said that on your homework, you're not clear about which things are vectors and which things are scalars. It's easier to tell us which things are matrices because we usually use capital letters. If you always stick with capital letters for matrices, lowercase for scalars and vectors, we're good with the matrices. But when you're lowercase, you have to distinguish which ones are vectors and which ones are scalars. So on the exam, on the free response problem, be sure to signify which ones are vectors, either by a line on the top or a line on the bottom or an arrow on the top. Those are three natural ways to do that. It's hard to do bold on your free response, but you could try it, I guess. But so yeah, be really careful because depending on things, if they're scalars or vectors, the mathematics is the same, right? Is different. They have different properties, so you can do certain things with them, or you can't do certain things with them. So you need to be clear. Okay, questions for me? Anything about the exam? Content on the exam? I asked you to look at some of the practice exams and bring problems. Does anyone have problems? Yes.
There was actually one, I don't remember what it was. I think it was on the first practice exam. I don't remember what the number was off the top of the head. But you basically had two vectors heading in this direction on the grid. And they asked you to subtract. So you had U and V, and then subtract U from V and ask which direction, what
right.
you had. Could you just go over that?
You bet. Let me pull it up. So while I'm doing this, you guys can be thinking about this, the first problem here. If I have a matrix and I cube it, and I get the zero matrix, is that matrix invertible or not? Okay, so be thinking about that. You can talk to your neighbor about that while I find this, pull up this exam. This is the one, right? Okay. All right, we'll do 12A here. So take 30 more seconds, think about the A, and then we'll dive to this other question. So. All right. So these kind of problems are the ones that tend to be hardest for students. Okay, they're not computational. Okay, there's not a straightforward procedure. It's testing your understanding of the concepts and the relationships and the properties of the mathematics that we've learned. So they're closely related to proofs. Like one of the reasons we ask you to do proofs is to practice reasoning through problems like this that we give you, and to become more fluent, although I've cut several of the proofs out this semester. It's one of the reasons we have you do proofs, is to help you with your reasoning through problems like this. So thumbs up if you think this is true, thumbs up if you think this is false. So a cubed is equal 0, then a is not invertible. Thumbs up if you say it's true, thumbs down if you say it's false. Okay, all the thumbs I see are up, I think. Okay, up or they're not being raised. That's true. The question is like, why? How could you reason through? You're on the exam, how would you reason through whether A was invertible or not? Yes?
One thing, I mean, what ran through my head thinking about this is that every invertible matrix is a product of elementary matrices with that central theorem or whatever it's called. So if a product of elementary matrices is invertible, right, that means, or in order for that statement to be false, and that would mean the zero matrix would have to be a product of invertible, or a product of elementary matrices. But there's no elementary matrix like transformation that you can do to get a row of zeros. So
Very nice. That's beautiful. Okay, way to use the power of the things we've talked about. So yeah, you thought, well, if it's invertible, there's lots of different ways to reason through this. Okay, so I'm sure a lot of you didn't think about that. That's okay. So if A is invertible, hey, what do I know about invertible matrices? Well, one of the things I know is I can write them as elementary matrices. So then A cubed I could write as just a big product of elementary matrices. And could I get 0 with elementary matrices? No, I couldn't. There's no row operation I can do on an invertible matrix and get a row of zeros. And so, hey, I think that's going to be true. Nice. Okay, someone else have another way to reason through this? Yes. Okay, so you picked a matrix that you knew would be true in this case. Like, hey, if A3 is the 0 matrix, then I cube it, I get the 0 matrix. But if you try to find the inverse matrix, I'm sorry, yeah, the inverse matrix, you have a problem because you end up with 1 over 0 minus 0 in the denominator for the determinant, which is undefined. Nice. Does A have to be the 0 matrix in this case? No. There are matrices that aren't 0 that you could cube and still get the 0 matrix. Okay, so one of the theorems, one of the things that you need to be careful of is that if A times B equals 0, then that doesn't mean that A or B is 0. Okay, that's not true. Okay, but this is a nice strategy to reason through this problem. Hey, I know it works for the 0 matrix. Hey, the 0 isn't invertible, so it's probably true for, you found one example where it's not invertible. Hey, so I'm going to say, yeah, that's true. So nice. Other ways, yes? Yeah, so you have A inverse times A times A times A equals 0, and you multiply A inverse on this side. Very nice. Yeah, so you keep multiplying on that side and you get I equals 0. Fantastic. That's awesome. Yeah, really nice. So you just keep multiplying A inverse on this side, or A inverse, assuming it's invertible, A inverse cubed on this side, and get A cubed. And then what happens with this side? Should have given myself more room. Yeah, you get the identity equals 0, which you know is false, so it's not true. Nice. Okay, other ways to reason through this? I'll give you one more that I find really powerful to reason through problems like this. Works really well for B too, and that is the theorem we proved the other day said that if I multiply 2 invertible matrices, I get an invertible matrix. And the opposite's also true, is that if you have a matrix that's an invertible matrix and you factor it down, then those factors have to be invertible matrices. So here, this 0 is not an invertible matrix. And so I factored it down here. I can't factor down a non-invertible matrix into invertible matrices. So So thinking about products, if I multiply invertible matrices, I'm always going to get invertible matrices. If I factor down an invertible matrix, I'm always going to factor it down into invertible matrices. If I factor down a non-invertible matrix, at least one of those factors has to be non-invertible. And since all three of these are, all of those factors are A, and one of them has to be non-invertible, then A has to be non-invertible. So that's another way to reason through those. Okay, back to this question. So for the given vectors u and v, which of the following vectors in standard position represent u minus v? So just think first about, what vector is u minus v? You can talk to your neighbor about what you pick here. All right. So hopefully we're confident enough that we're going to go, hopefully you know that, hey, we have to go from head to head here. The question is just whether it goes from here to there or there to here. And it does say in standard position, so the vector's not going to be up here actually. It's going to be, the tail's going to be there, and so we're going to either point from here that way or here this way. Okay, so so which is it? Is the head going to be pointing up this way, or is it going? Oh, yeah. Is the vector going to be pointing up this way, or is it going to be pointing down to the right? So just use your arm and say if it's going to. If you vote up this way, go like this. If you vote down, go like that. Okay. So you guys all Nazis? What do you have Hitler for? Okay, I'm just kidding. All right. So lots of this. Okay. Another question is why, and how would you know? So when you do subtracts, you can remember that you're subtracting the tail. When you do this, you're always there. This here is where your tail is going to start. So it's going to be tail to head. But suppose you forgot that. You're on the exam. You're like, oh, what do I get? Oh, is it going to be that way? Is it going to be down this way? I can't remember. Well, here's one thing you can do. If you're good with addition, I hope you're all good with addition. You know, it was a long time ago. You've been doing it for a really long time. What about v plus u minus v? This is the one I'm trying to figure out. I'm going to add a v so these cancel out, and I know I just get the u. So if you understand what happens with vector addition on a graph, then you can reason through this. How does that help? Well, I know if I had vector addition, I use one vector, then I follow the other vector from that head, and I know I better end up with u. So if I do v, where else do I have to go to get to u? I have to go up this way. So now I know. Yep, it's got to go that way. If it was this one, I wouldn't end up at u, right? So there are always ways to reason through this if you understand the mathematics. You're good with the connections. So, okay, I know it's easier said than done, right? Easy for me to do it and say it, but so in this case, looks like A would be the answer, right? So, okay. All right. So if you have other questions, we can type in the other questions. I can also pull up that the rest of that number 12 we were working on. So what should we do? Yes. On this first exam? Okay, so let me let everyone take a look at this and let you decide how, try to figure out what these are, and then we'll go over it as a class. This is another mark all that are true. By the way, just really fast, on the exam, the mark all that are true will have a clover sign, a club sign right by the number, so you'll know, hey, this is a mark all that's true. If it doesn't have that, it's just a regular multiple choice, and only one of them will be true. But here, you could have multiple correct answers. So, oops. All right, take about 30 more seconds. Okay. So true or false again, we'll do thumbs up, thumbs down. If you don't know, you can just go thumb sideways, so it gives me an idea about, see how confident you guys are as a class. So A, the sum of rank of a matrix A and the number of free variables is equal to the number of columns of A. So thumbs up if you say true, thumbs down if you say false, thumb sideways if you don't know. Okay, see a whole bunch of thumbs up. Good. Yep, that's a theorem. I think they call it the rank theorem in the book. Okay, all of the variables either have to be a pivot column, or each of the columns either has to be a pivot column or a free variable column. So they call it leading column or free variable column. So yeah, so the sum of the rank and the rank of the matrix is the number of pivot columns you have. So pivot columns or pivot rows. So the sum of the rank of the matrix A and the number of free variables is equal to the number of columns A? Yes, because you either got to be one or the other, so you got to add up to the total. If a linear system with the same number of equations as variables has a unique solution, the Gauss-Jordan elimination will give an augmented matrix of the form this. I think they also meant like you should have dot, dot, dots, some others around here. You don't just have those, so I think they missed a few dot, dot, dots. But they mean a square matrix over here with ones down the diagonal, 0 everywhere else on this side, and then some numbers over there. So thumbs up if you say it's true, thumbs down if you say it's false, thumbs to the left or right if you're not sure about what's going on. Okay. Thumbs in your ear if you'd rather be skiing. Okay, just kidding. All right. Yeah, this is true. So a lot of thumbs up. Good job. Why? Well, in the invertible matrix theorem, one of the things that we know is equivalent to the invertible matrix is that this system has a unique solution. So, so this says with the same number of equations as variables, so we have a square matrix over here, has a unique solution, the Gauss-Jordan elimination will give an augmented matrix of the form. So if it has a unique solution, then that's equivalent to this matrix here being invertible, and an invertible matrix is always row reduced to the identity matrix. It's row equivalent to the identity matrix. So yes, that's true. Seth.
It's like an augmented homogeneous all zero matrix, not a counterexample then?
Yeah, so homogeneous system is you're augmenting it with 0.
Right.
So that gets us to C. But yeah, yeah, this isn't homogeneous necessarily.
But wouldn't that be a counterexample so it would be false or no?
No, because so that question was, wouldn't it be counterexample if this was homogeneous? No, because 0 is still some numbers. So yeah. So you can still have all those 0 over there. That's okay. So it is possible. So now we're at C. It's possible to construct an inconsistent system of linear homogeneous systems of equations. Thumbs up if it's true. Thumbs down if it's false. Thumbs sideways if you're not sure. Okay, lots of thumbs down. Good job. So why not? Well, if you've got a homogeneous system, then you've got a whole bunch of zeros over there, right? All these are zeros, and no matter what you row reduce this to, the only way to get an inconsistent system is to have a row of zeros at the bottom on the left-hand side, and this to be non-zero. That's the only way. That's one way of thinking about it. Like, that's the only way to get an inconsistent solution is to get a row of zeros and then a non-zero. Okay? Go New Zealand. But if these are all zeros, then you're all right. And another way of thinking about that is you're saying, what linear combination of these columns can I make and get all the 0 vector? Well, you can always take 0 of the first column and 0 of the second column and 0 of the third column. You just take 0 of all those and you get that. There's always a solution. So, yeah. Okay. D, if the augmented matrix A augment B has 5 rows and 11 columns, so A then would have 10 columns. B would be the 11th column. Okay, so you got to be a little careful with that. Then it is not possible for the number of free variables to be equal to 3. So thumbs up if you say it's true, thumbs down if you say it's false. Yeah, thumbs sideways if you're not sure. Okay. All right. So this is true. Okay. It is true that it's not possible. It's kind of a weird thing. So it's true that it doesn't work. So how to think about this? Well, you can think about this as with the rank theorem, that all of your free variables and your pivot columns have to add up to the rank of the matrix. So if I have an augmented matrix here and I have 10 columns, and what did it say in the problem? It was 5 by 10 and, oh yeah, that's all I need to know. It's 5 by 10. So 5 by 11, but 10 of those will be in the matrix here. So what's the fewest number of free variables I could have? Yeah, hold up on your hand. That's a good idea. So 5, 4, 3, 2, 1. What is it? 6, 7, 8, 9, 10. Okay, sign language. All right, 5. Yep, good job. High five. Okay, why? Because if I row reduce, the most number of pivot columns I can get is 1 for each row. I can have a pivot position for each row because I have 5 here. The minimum number of these is what I can get in terms of the number of pivot positions at the most. So I could have 1, 1, 1, 1, 1, but then that gives me 5 free variables. And I can get fewer than that, right? If I didn't have a pivot position there, then I'd have 6. If I didn't have a position there, I'd have 7. If I didn't have a position, but the fewest I can get, is 5. So I can't have 3. Okay? Questions on that? All right, study hard and have fun.